Hello, today we are going to be starting our next unit, which is chemical equilibrium. This is chapter 15 in our textbooks. And once we take a look at chapter 15, we will also be doing parts of 17 and 19 in this unit. Our video today deals with a lot of our basics of equilibrium. So this is generally going to be a review of Regents level equilibrium. So hopefully you remember that if we have, let's say, a basic reaction of A turns into B. So if the arrow is written like that, it would be a one direction reaction. So A would get consumed and produce B. For many reactions, though, once you accumulate a certain amount of B, then it will start the reverse reaction occurring and you will make back A. Once you get to equilibrium, that is defined as the rate of the forward reaction being equal to the rate of the reverse reaction, hence why we use the double arrows. And actually, the arrows are usually shown a little bit differently than how I drew that first one. They're usually shown like that, or depending on the font that I'm using, sometimes we would just have a double arrow too. Now, one of the other parts of our definition is that once we reach equilibrium, the concentration of the products and the reactants remains constant, not equal, constant. So, for example, let's say that we have 10 molecules of A and 6 molecules of B. If we are at equilibrium, then every time an A reacts, it turns into B. So it would be 9 and 7. But then if we're at equilibrium, the reverse reaction also would occur. So 1B would get consumed and 1A would get produced. Therefore, we would be maintaining the concentrations. And notice they are not equal to each other. We could easily show this with a glass of ice water. So if we are at 0 degrees Celsius, and if our ice water has, a couple of ice cubes in there, if we are at equilibrium, H2O solid to H2O liquid, then every time an ice cube melts, a new one has to form. So if that ice cube melts and goes away, then if we are at equilibrium, a new ice cube would need to form. So you would keep 3 ice cubes in there. Notice the amount of ice and water are not equal to each other. So they do not need to be equal to each other, but the amounts remain constant. And yes, I realize that the ice would be floating and not towards the middle or bottom half of my glass of water, but we all know that my artistic skills are severely lacking. So when we talked about equilibrium in Regents chemistry, we talked a lot about different examples, and we talked about how homeostasis is your body maintaining equilibrium. It is a dynamic equilibrium, meaning that even though it might not appear outwardly like much change is happening, lots is happening behind the scenes. So there are reactions that are occurring. We are forming products, we are reforming the reactants, but once the amounts stay constant, it kind of looks like nothing is happening because there's no net change in the concentrations once we reach equilibrium. Another example that we used was our home heating systems. So as long as our heat is functioning properly, our thermostat and furnace work together to keep our house a nice, comfortable, 67, 70 degrees Fahrenheit. But your heat has to work to maintain that temperature. All right, graphically, a lot of times we look at how our concentrations change over time. With both of these graphs, we see that we reach equilibrium once we get to a constant concentration. So once we reach about this point here on that first graph, that would be equilibrium because then the levels stay constant. On the second graph, that is showing us the rate of the forward, shown with the F, and rate of the reverse, shown with R. We reach equilibrium when our rate of our forward is equal to the rate of the reverse. So once the rates become equal to each other, that's when we would get to equilibrium. All right, this just shows us another way to look at our equilibrium. Remember, equilibrium, rate of the forward is equal to the rate of the reverse reaction, and the amounts will remain constant, or the concentration remains constant once we reach equilibrium. So in picture A, if we look at that, we have 1, 2, 3, 4, 5, 6, 7 water molecules. So we're starting with 7 water molecules. And we also have 7 carbon monoxide molecules. Now, these just happen to be put into the container in a 1-to-1 ratio. They would not have to. Any amount could be the starting amount. Then at time B, we now have 1, 2, 3, 4, 5 water molecules remaining. And we have 1, 2, 3, 4, 5 carbon monoxide molecules. And we have 2 hydrogen molecules. And we also have 2 carbon dioxide molecules, which makes sense because they are being produced in a 1-to-1 ratio. Once we get to time C, then we obviously see that we have a lot more carbon dioxide and hydrogen gas. We now only have 2 water molecules. We also only have 2 molecules of carbon monoxide. We have 1, 2, 3, 4, 5, 6 molecules of hydrogen gas and 6 molecules of carbon dioxide gas. In picture D, we still have 2 water molecules. We still have 2 carbon monoxide molecules. And if we count, we have 6 hydrogen molecules and 6 carbon dioxide molecules. So we have reached equilibrium at C because our amounts are now remaining constant. So C and D is showing us that we are now at equilibrium. Our last note about equilibrium is that in order for a reaction to be able to reach equilibrium, we must have a process that is reversible. So if you have a reaction that is not able to proceed in the reverse direction, then that process can obviously not reach equilibrium. So it's got to be able to proceed in both directions. And technically, in order to do that, it has to be a closed system so that you are not introducing new things or losing substances. Like if you had a gas and it wasn't in a closed system, then you would be losing your gas molecules. So it's got to be able to proceed in both directions and has to be a closed system in order to be able to reach equilibrium.